Try to figure out where you are. So here's where we are. We're slowly making our way through the various kinds of surveys and how they're connected to different physical properties. So we start off with magnetic susceptibility. Is the magnetic survey. Okay. Then we get seismic, looking for layers or what the P wave, Q wave velocity is. Very important for geotechnical engineering. Then we did electrical permittivity, ground penetrating radar. So this is the ability for a molecule to kind of rotate within the context of electric field. And then we looked at the resistivity or electrical conductivity, and we did it with a couple of techniques. DC resistivity. DC resistivity is pretty easy. But there is one concept that some people got confused about. I just want to make that concept clear now. So in DC resistivity, you put a current into the ground. Now we've got an electrical resistivity. The current then just flows out. This is a steady state current. Imagine what you have if you have a battery, right? So you got some resistance in here, and maybe, I don't know, it doesn't matter. But you got this resistor in here. And the current flows through here. It's continuous. It's not like it's changing. It's not like a current is flowing. I mean, the current flows, but it's not like a wave. It's not like a GPR wave. So that's a different way of propagating energy. So in GPR, we talked about waves going. In seismic, we talked about waves going. These are sort of time-varying phenomena. In DC resistivity, we just simply had, in fact, remember we had like a little light bulb? Okay. As soon as we close that circuit, we got a constant current going. So there's no waves that are going through that. That's the concept. Where we do get waves is when we consider the EM portion of the electromagnetism. So you're changing the current in some transmitter, and then you get waves that are going out. And depending upon how fast you're changing them, you can actually get into this GPR range. So remember, I wrote this line here. This is frequency, and here was zero frequency. So F equals 0. So this is DC. Nothing changes in time. It's steady state. Sure, there's electrons moving, but there's no waves. And then at the other scale here, maybe 10 to the 9th, which actually is big, we had the GPR. And here was definitely waves. And then most of the stuff that we're interested in recently, the EM phenomenon, are from some small frequency, let's say 10 to the -2, to maybe 10 to the 1st. Each of these kinds of waves or signals has a different way of kind of interrogating. From the process of your perspective, and I can really appreciate, like, there's just a lot of stuff going on in this course, right? Just because we've got all of these different techniques in another world, it would actually be nice just to have a whole semester on one of these guys, right? We don't have that luxury. So there's a lot of new things that are coming in. There's new words, concepts, and things like that. The most complicated is actually this guy here, the EM part of it. And we're now pretty much, well, we are done that, except you're going to have a lab on Monday and Tuesday. And that's going to refresh a few things. But then basically everything is the one thing that I haven't talked about, and that turns out to be very important, is chargeability. So that's a new kind of physical property, and how many people have heard of induced polarization or IP or anybody? Yeah. What were you doing?
They wanted to do it for mineral exploration.
Mm-hmm. It's one of the mainstays actually for mineral exploration, especially if you're looking for sulfides. It's hard to use any of these other techniques, but charge building just kind of likes it somehow. So, first of all, let's see, Samantha, we need to give Leah and Kyle a star because they're the only two people. Oh, no, they're gone. Yes! Go ahead and ask your question. Okay. There is, at the end, there's one other lab that said there's no name. So, somebody could try to find their name. And then we can record it. Okay. So I want to talk about induced polarization. So this actually looks familiar. Right? This is the same kind of thing that we did in DC resistivity. We put a current into the ground, and that current went through a body, and then we measured the electric potential. And these pictures are very similar to what we had before. Here's a pseudo section. Here's a target in there. The difference between this and what we did before is that the electrical conductivity of this whole unit is the same, but there is a difference in the chargeability. So that's what now we're going to focus on. So our physical property is effectively going to be chargeability. And chargeability is intimately connected with the electrical conductivity. I'll explain a little bit more about that later. But first of all, we need to refresh your mind about the electrical resistivity of rocks. Remember this diagram. So rocks that are low resistivity are these acid sulfides, high resistivities are metamorphic rocks. The thing about conductivity or resistivity is that you can measure these things in the lab. What you do is you take a little sample. In fact, you did that, okay, in the lab. You take a little bit of a sample, you put it in this sample holder here, and then you put in a known voltage, and you measure the current, and then you can actually extract from that the resistance of this sample, and hence then the resistivity. Okay, so you remember how you did that. It turns out that it depends, the number that you get up here actually depends upon the frequency of the transmitter that you're using. So if I put on in here instead of a battery, let's suppose I have a little generator that I hook up. And I make some really low frequency, so 10 to the minus 4 hertz or something like that. It turns out that I'm going to get a resistance here that is going to be reflective of what's happening in this particular sample. Let me try to explain one more thing. We're going to put in, let's say, a current that looks like this. So here's our input current. And then we're going to get just the same as we talked about previously. We're going to get a measured current that's going to go in this system. It's going to have something that looks like that. So there's going to be a little bit of a phase shift. And the result of that is that if I plot it up, so whenever I have a little phase shift, I can always talk about the real and the imaginary parts and something like that, just the same as we did now. If I plot frequency along this axis, and I plot the real part of the conductivity at very low frequencies. It's got some conductivity. And then at higher frequencies, it's got a different conductivity. So it's like taking a rock. If I did a measurement at, let's say, 100 hertz, maybe the rock has a resistivity of 10 ohm meters. If I did the experiment at 1,000 hertz, maybe it's no longer, what is it, 10? Maybe it's like 9 ohm meters or 8 ohm meters, or something like that. So the thing is that the conductivity of the resistivity is actually dependent upon the frequency. So that's kind of interesting. So instead of having a rock or a little unit and say, well, this is 9 ohm meters, then it actually depends upon what sort of frequency you're measuring things at as to whether it's 8 ohm meters or 8.5 or 9 or 9. So where could that process actually make a difference? Well, one place is in mineral exploration. Another place is in geotechnical work. There's a lot of work now, especially in old hydrocarbon dumps or places where there's been contaminants. So the electrical resistivity is frequency dependent. Not sure if people have heard about seafloor mining or minerals on the ocean floor. That's a topic that's coming up. But you have sulfides that exist on the ocean floor. Groundwater, in trying to characterize the background of material. I talked to you about those experiments that Saudi's going to be doing when he goes to Stanford and trying to characterize that near surface region. You've got clays, you've got silts and sandstones and things like that. You want to differentiate between those two. And certain materials like clays have this frequency-dependent resistivity. And then also permafrost. So something else that has a signal that could be that could be recorded, that we get some information out if we could know what the electrical conductivity is. So chargeability is a microscopic phenomenon. I mean, what you're seeing here is very small fibers. This is a scanning electron microscope image or something. There's just 100 microns that are here. You can see there's lots of surface area. There's a lot of texture and porosity that's going on here. The fact that the resistivity changes with frequency comes about from microscopic processes that happen. Nevertheless, we can still see something that is macroscopic, and that's encapsulated in here. So suppose that we've got an Earth that's not chargeable, and we have a source for it. So this is what we were doing before. So this is a current that goes on, stays on, goes off, stays off, and then we do it the other direction. So that's our current source. And then our electric potentials follow exactly the same kind of character. Looks exactly like that. So the thing that we're really interested in here is what the value of that potential is. We convert that, we are DC experiment, convert it to electrical. If the material is chargeable, however, something really interesting happens. I turn this current on, okay? And then if I measure the voltage, so the voltage initially rises just the same as it would, but then it continues to build up. So in the case where the Earth material is just not chargeable, I turn the current on, and then my voltage goes up the same. So this is my current, and this is my voltage, okay? If I have a chargeable material, however, the moment that I turn this current on, I then get an increase in voltage, but then the oddest thing happens. It just continues to increase, increases, and then it gradually asymptotes out at some point. So I've got this current turned on, and my voltage increases. Then if I turn the current off, this thing drops down suddenly, but not to zero. It drops down to some point, and then it just continues to decay. So it's a very unusual phenomenon. It was totally unexpected when it was first found back in the 50s. And at that point, it was just something called overload, because it's like something odd is really happening. Yeah?
So it's just like delaying.
Yeah, it's not, well, it's delaying and getting to this and
Is
value.
the value the same as what it would be on the top there?
No.
No.
So this is the value that you get
Okay.
if it was not chargeable. So if it is chargeable, then you get
It's higher value than
a
normal.
higher value. Exactly. So if we look at how we're going to measure this stuff, it's chargeability. These units will make a little bit more sense later on. They're actually in terms of time, so these are milliseconds. And things like pyrite, chalcopyrite, copper, very high chargeabilities. And then stuff that's becomes lower as far as the minerals go. And material type sulfides are the big kids on the block. They're very chargeable, and clays and graphites, those have also a high chargeability. So all kinds of rocks have got a range of chargeability, and that means that, okay, maybe we could do an experiment and we could find, whether something is a sulfide, or maybe it's a granite or a limestone or something like that. So that would be good. That would be useful. So the physical property I said is then effectively the electrical conductivity or resistivity is just that it's changing as a function of time. And the definition of the chargeability, something called intrinsic charge, is the difference between when frequency is infinite, so this value here, and when frequency is zero, the DC value. And the definition for chargeability is the difference between those two things divided by sigma. So in other words, if I look at the real part of the conductivity as a function of frequency, at the DC level I get something that looks like this. So this would be sigma 0, so this is frequency 0. And then as I increase frequency, it kind of goes up to something like this, and this is sigma infinity. Then I'm going to say, well, what's my chargeability? My chargeability is really kind of related to the amount of change here. I want to normalize it by something. So the chargeability is sigma infinity minus sigma 0 divided by sigma infinity. Yeah. Oh, come on. Yeah, so this is something called intrinsic. So first, that's a good point. So what's going to be the units of this? No, units, right? So sigma over sigma. So it's dimensionless. What's going to be the size of the numbers? Could be 0 to 1. Okay, so chargeability is in the range 0 to 1. Okay, so that's an important, those are important concepts, right? So if a rock is chargeable, then that means that the electrical conductivity changes with frequency. It depends what frequency I'm using to measure that as to what number I'm going to get up. And the amount of that, or the size of that chargeability, kind of depends upon the relative change of the conductivity between 0. Okay, so what is going on, and how do we think about it? the easiest way to do it, like, it's like for everything else in life, we need to have some kind of a mental model. And here is the simplest one that exists, and it actually has a lot of a good physical basis. Maybe I'll just sketch it out. So now imagine we're looking in kind of a microscopic scale, and let's suppose we're looking inside the Earth, and you guys are very much into fluid and porous media and stuff like that. So just imagine that you've got, a little conduit in here. So maybe this is just microns here. And we've got maybe a pore throat. So this is, 1,000th of a centimeter or something. Right? We're talking pretty small. And we've got, let's say, some kind of boundary. Maybe that's a clay particle on this side, and a clay particle on that side. And then we've got fluid in here. So this is going to be fluid. And this is, let's say, clay. That's clay. And we've got some kind of. In that fluid, there's going to be an ionic, well, there are going to be ions, positive and negative. So these might be sort of positive ions here. So it's going to be electrically neutral. So we just got, our initial state is that we've got an electrically neutral fluid that's sitting in a pore throat. Okay, what is now going to happen if I put on an electric field in this case? So now let's make, I've got an electric field that's going like this. Okay? So first of all, if I think about an electric field, how could I generate something like that if you're thinking about making an electric field with charges or something? Anybody? That? Maybe the easiest way to think about an electric field going in this direction is if I just thought about some great big positive charge here, right? Remember, if I've got a positive charge, and the electric field will go out like this. So I've got an electric force that's kind of pushing everything this way. Okay? Good. Now let's think about what's going to happen here. How are these ions going to rearrange themselves in the presence of this electric field? Yeah, Lynn?
You get accumulation of positives and negatives on it.
Right, and who's going where? Right, so the positive is going to feel repelled from this. So that's going to mean, you're going to try to get positives this way, right? And these positives are going to try to go there. And then the negatives, these guys want to come back here, right? And these, yeah, so we've got negatives that are coming in here. So at the end of the day, you have a little bit of what you've got up in here. You've got an accumulation of positive ions here, an accumulation of negative ions there. Okay? But now once I've got that, now I can take a step back and say, okay, well, what do I have here? Well, it's just like I've got this big accumulation of charge with some positive values here and negative values here. And that, of course, is going to give me an electric potential. So if I have some positive charge here and negative charge here, and I'm sitting up here with my voltmeter, I'm going to measure the electric potential for that. So that is really the mental model and the essence of what's going on. We're going to start with an Earth that is, it's going to probably have a lot of porosity and stuff like that. And we're going to put on this electric field. Just think about putting a battery on here, some kind of charge. Positive charges are going to try to go this way, negative charges go this way. But then you've got these pore throats. So you've got regions that, those ions simply can't move through, so they just get kind of blocked up, piled up there. And then the end result of that is you get this accumulation, positive and negative charges. And then that's going to give us a electric potential. So that's a fairly straightforward process, and it's a really good mental model for a number of reasons that I'll show you in a second. Remember I talked to you about this, this overmotion. Remember I said you turn the current on, and there's this initial rise in voltage, and then it gradually accumulates to a steady state, then you turn it off, and it comes down like this. I think we can now understand this by just this kind of mental model that we have here. So you initially start in this kind of neutral position. Then you put an electric field on here. And now, initially, there's a lot of charges that are pretty easy to move. But then after a while, you can't put any more positive charges in here, because if you try to put another positive charge in here, it's going to get repelled by these guys, and so you end up with an equilibrium. So the upshot is that initially, it's pretty easy to build those charges up, and then they gradually kind of clog up and hit their final value, and they sort of end up in a steady state. And then, of course, you see the same thing happen the other way around. Well, if you take that force off, everything just kind of wants to go back, and the first accumulated charges is pretty easy, but then the other guys have got to gradually make their way back through the fluids, and it takes a while. Okay, so this is yes.
The matter, the surface there is like negatively charged with that positive face there. It could just be the other way around.
Oh, what I've shown up here, it turns out it's kind of interesting. I don't know, do you guys look at clay particles a lot? So clay particles, a clay particle actually has a net negative charge. So the reason that was for that was to kind of represent that. So it has a net negative charge, and then there's a number of ions that get fixed there because you've got strong and negatives. So you've got this fixed layer of positive charges that come there, usually because there's clay layer. So that doesn't really enter into our discussion, but it actually turns out to be very important later on if you go into something that's really trying to understand what's going on. No, and the bottom line is, if you got rid of the negative and the positive, then you still have effectively what I have. So the effect of chargeability was really to alter the conductivity. If I have a conductivity at infinite frequency, and then I reduce that frequency down to 0, then there's some differential in that bulk conductivity. So effectively, if really a chargeable material has got an end conductivity that is perturbed from the original conductivity by this chargeability eta, where this was that intrinsic value. And then here was the definition of an IP datum, which is the difference between these two values here divided by this value. So that's not directly measurable. It would be kind of nice if we could do an experiment in which we turn the current on, we measure this stuff, and then turned it off. So here's what we're left with after we turn it off is just secondary potentials that are a result of just all these charges that are accumulating. We unfortunately can't reach that value, can't see that, but we will be measuring something a bit later on. And in fact, the things that we do measure can have a whole variety of forms. We could measure just the value of the potential at any particular time in here. So we're going to say that all of this kind of decaying potentials that we see, they're all due to those accumulated charges. We're going to call that the secondary potential. So that's why this is an S here. So we could measure the secondary potential at a particular time, or we could do the integral of that over a different time channel, or we could normalize it. And all of those things would then have different units. But the bottom line is that anything that we could possibly measure that's somehow connected with this decay here, which is related to this buildup of those charges, that's good enough. That's somehow related to the fact that this rock can accumulate charge, or if you like, that the rock can really act like a capacitor. We can do it, that's in time domain. We can also do it in frequency domain. One of the things is that if you had a source current that looks like this, and then you measured the potentials, it might look like this. There's a little bit of a phase lag here. And so that is, again, due to accumulation of charges. So that sometimes you'll see frequency domain done. And these values here would then be in terms of radians, or because it's small, usually milliradians. So the bottom line with all of this is that effectively chargeability is sort of perturbing the conductivity. Maybe 10%, 5%, or something like that. And without going into details, that allows us to make a relationship between any IP data that we have and this chargeability. So, sort of summary for the IP data. In the time domain, here's your curve, kind of looks like that. Anything that we measure on here is a valid representation of an IP datum. So it could be dimensionless, it could be milliseconds. And in the frequency domain, it's phase shift, and all of these problems are kind of linear relationships between what we call pseudo-chargeability and. So let me show you now how all this is going to work out in practice. The IP data are required at exactly the same time as the DC resistivity, right? Because you can see it's the same parameter. So we're going to, we got our, here's our A, here's our B, here's our M, here's our N. So here we're going to measure the voltage. And if we turn the current on, that looks like this, and then turn it off, so this is T, then the voltage that we measure looks like this, this, and this is the data that we would obtain and put that into our formula to calculate the apparent resistivity. However, if we've got chargeability, then really nothing happens except that this curve here continues to go up, and then when we turn it off, it drops down, and then decays. So it just means that you use exactly the same equipment, but you're just measuring different things. In the DC experiment, you're basically trying to measure this value. In the chargeability experiment, the IP, you want to measure something out here. So you don't have to do anything different. You just have your equipment out there, and it's just measuring these voltages in the off time. So during the time that the transmitter is off, anything that you measure here is a reflection that charges have been built up. Okay, so that's the experiment, and hence, what they will often do is they'll sometimes refer to this as a DC IP experiment. Or in some cases now, especially if you're looking for sulfides, the contractor will go out and say, oh, I'm going to do an IP experiment. But if he does an IP experiment, he's clearly doing the DC. And so you're going to see both. So then as far as surveys, we can have all the things that we had before. We have a Wagner, Schlumberger, some kind of gradient, all these guys. And the data, oh, fix this up. Sorry. So the data are going to be plotted in exactly the same way as we had done before. So we can plot it in a pseudo section. So each datum that we have, and it could be one that's milliseconds, milliradians, millivolts per volt, whatever. So any data could be plotted in this pseudo section form. And of course, we can then go ahead and just do the continual. So now we're just kind of collecting data, plotting it in exactly the same way that we build up the resistivity pseudo sections. And then we get something that looks like this. But this is now called an apparent chargeability map. So it kind of looks the same, but this is now apparent chargeability. So now let's see what we have. So here's a block. So everything here is the same. Same conductivity, but the block is chargeable. And now we go ahead and we're going to do that IP experiment over top of it. We're going to get IP data, we're going to plot it up, and we get this pseudo section. That looks pretty similar to what we did before. And again, if we now have other pieces of stuff in here now, especially we're talking about chargeable materials. So maybe it's clays. You've got little bits of graphite that are sitting up here, things that are chargeable. And then look now what that does to your data, to your pseudo section. Again, it screws it up just the same as the DC experiment got screwed up. And then if we have this example where we've got sort of a valley but now two chargeable bodies, again, the apparent chargeability map looks like this. And what people have traditionally done is sort of drill on the chargeability highs, and again, if you do that, you totally miss these two chargeable. So that means you can't just stick with looking data, you got to invert them. And here's what we're going to do to invert them. It's a two-stage process. So the very first thing is that we're going to go out and we're going to collect the DCIP data. Then we're going to take the DC data. Okay, so those were final potentials that we had. So here was our current, right? And then here's our potentials. We're going to take this guy here, whatever that number is, and convert that to an apparent resistivity. Okay? And then we're going to take those DC data, we're going to invert them, we're going to get conductivity or resistivity. Okay, so that's the DC experiment. We did that. That was 3 weeks ago. Okay? So go out, DC data, and invert it. Good to go. Now we're interested in looking at this stuff here, these secondary fields that are coming from those charges that are built up. And we need to have some way of relating things. And we're going to use the electrical conductivity that we got from here and build a mapping between our IP data and this, whatever we're measuring, the pseudo chargeability. It's a little bit of a step, but the essence is here. Remember, there's basically two things. One, as I said, the chargeability kind of altered the electrical conductivity. So if something is chargeable, then it's equal to the conductivity at infinite frequency times 1 minus eta. And eta was a small number between 0 and 0.2 or something like that. So that kind of established a relationship between any IP data. So we can write any IP data is equal to some matrix J times whatever pseudo charge relative. So if this happened to be in milliseconds, then your end result here would be in milliseconds. This is in milliradians, this is in milliradians. But this guy here actually depends upon the electrical conductivity from the DC. Okay? So we've collected the DC data, we've inverted it, got a conductivity, and with that, we're actually able to make that relationship between the IP data and chargeability. And now once we've got that, we can invert for chargeability and get out something that looks like this. So it's like another physical property, but it's a two-stage process. If you're going to invert IP data, you first of all have to get the electrical conductivity. And then we could do a second inversion to recover charge. So now let's look at a couple of examples. So if we do this case back here with the buried prism, we have this chargeable block. Here's our data. Here's the recovered chargeability, and here's the predicted data. So you see we've actually done a pretty good job at getting that chargeability. More interesting example is look at this, where you've got all this geologic, perhaps jump, perhaps noise, I don't know, that's sort of sitting up here. That's completely distorting your IP data. But if you invert that, you get a recovered chargeability that has got the target that you're looking for plus these guys. And then if we come back to this example, then we've got two blocks here. Here's our pseudo section inverted. We get out two things. So that allows us now to unravel things and to kind of work with a full both DC and IP experiment. So there's a whole bunch of examples that people have been using in practice. I'll be able to show you a couple of them. I don't think it's worthwhile starting today, but you remember when we did the DC resistivity, I showed you a picture. It's a place called Mount Isa in Australia, and we had all of these pseudo sections, and we were able to take that, we inverted that, and we got electrical conductivity. And then show this great big geologic unit that was coming through, which was kind of nice in a way, but it wasn't really the mineralized target that we were. So what we're going to do is we're going to go back to that and now do the DC IP experiment. And then we're going to see if we can't pull out something that's chargeable. And that chargeability will also be connected with the organization. The other case history that I want to show you, and I'm not sure whether geotechnical, if you guys can illuminate me on it, is are waste dumps like kind of an issue for geotechnical engineering? I mean, trying to find out, okay, where the waste dump is, how to characterize it, whether it's got leachate that's coming out of it, or are these issues that are relevant here? Any particular example?
Leachate, yes. When my saying you manage to pass on, you fill it up, layer it in
Yeah, so one of the really nice examples that they have, so suppose you got some kind of tailings over here, and so those tailings might have sulfides, right? But they also have all kinds of acids and stuff like this, and then you can get, kind of leachate that comes out of here. The leachates are usually very conductive. You've got a lot of total dissolved ions in it. So this stuff comes out as being really conductive. And this material in here is conductive, but it's also chargeable. So tatum sponges are one of them. In Europe, when we went there and went to various places, there one of the big ticket items is just waste dumps. I mean, because in times people would sort of build a city over this kind of a region, right? And then they say, oh, let's put my waste dump sort of out here, so maybe that's a kilometer away. And then a little bit later, the building, the area of the city kind of gets built up, and so after a while you find out, wait a minute, I just built on a waste dump, right? Where the hell is this stuff, and what do I do? And so trying to figure out where the waste dumps are, how bad they are, this actually turns out to be a pretty important problem. So we're seeing that now a lot more in the United States. I'll show you an example from Tucson. And then we're seeing a lot in Europe. Canada's a pretty big place. So there's still lots of places you can put your waste and not be concerned about it now. 50 years down the road, that might be a different issue. But there's this connection between waste and chargeability that's usually. So we'll pick up a couple of those case histories, and then we'll finish up sort of like the DC IP. We'll do that on